October 12, 1944. Captain Chuck Yeager levels his P-51 Mustang through the crisp German sky near Lechfeld Airfield. Below him, the enemy runway stretches like a concrete scar across the Bavarian landscape. What he sees next defies everything he knows about warfare. The Me-262s strike with surgical precision, their four 30mm cannons shredding B-17 flying fortresses before vanishing into the clouds. In just minutes, entire squadrons disappear from radar screens. The mathematical reality is brutal. At current loss rates, the Allied bombing campaign, the cornerstone of victory in Europe, faces catastrophic failure. June 19, 1944. The Battle of the Philippine Sea. In 12 hours of combat, American anti-aircraft guns destroy 346 Japanese aircraft. Not with the thousands of shells traditional doctrine demands, but with surgical precision that leaves enemy pilots stunned. Japanese pilots radio in disbelief. American shells explode without hitting anything. The secret weapon responsible for this carnage remains classified at the highest levels, protected as jealously as the Manhattan Project itself. Only a handful of men know its true designation, the VT proximity fuse. And the man who made it possible had no formal weapons training, no military background, and faced near-universal rejection from America's most brilliant minds. His name was Merle Tuve. He was about to revolutionize warfare forever, if he could survive the bureaucrats trying to destroy him. September 3, 1939. Britain declares war on Nazi Germany, and the world's deadliest guessing game begins. Every anti-aircraft gun from London to Pearl Harbor operates on the same primitive principle. Aim where you think the enemy will be. Set a timer fuse for when you hope your shell arrives, and pray. The mathematics are unforgiving. A traditional time-fused shell must be set to explode at precisely the right altitude. Too high, and the fragments scatter harmlessly. Too low, and the aircraft simply flies over the explosion. Calculating this intersection requires three variables that change every second: aircraft speed, direction, and altitude. Get anyone wrong, and you've just wasted expensive ammunition while enemy bombers continue their deadly mission. British Rear Admiral Charles Phillips stares at the statistics in his London office and sees the coming apocalypse. In the First World War, British guns fired 52,000 rounds for every German aircraft destroyed. New German planes fly twice as fast, at 3 times the altitude. The mathematical projection is terrifying: 150,000 rounds per kill. At this rate, Britain will exhaust her ammunition stockpiles long before making a meaningful dent in the Luftwaffe. Worse, German industrial capacity can produce aircraft faster than British guns can destroy them. The Battle of Britain looms, and British anti-aircraft defense remains essentially unchanged since 1918. American observers reach similar conclusions. Colonel Harold George, analyzing pre-war exercises, delivers a sobering assessment to the War Department. Current anti-aircraft effectiveness approaches statistical insignificance. Naval gunnery trials confirm the nightmare. Against high-speed targets, American ships would need to carry more ammunition than fuel to achieve meaningful defensive capability. The scientific community rallies to the challenge. Leading physicists propose exotic solutions: proximity detectors using light beams, magnetic field sensors, even primitive computers to calculate firing solutions. Each faces insurmountable technical hurdles. Vacuum tubes, the foundation of 1940s electronics, are fragile glass structures never designed to survive the 20,000 G acceleration of artillery firing. Most shatter instantly. Dr. James Van Allen at Johns Hopkins University attempts to ruggedize electronic components for ballistic applications. His first prototypes explode during ground testing. The electronics simply cannot withstand the violence of propellant ignition. Even if the components survive firing, they must then function in the chaos of aerial combat. Temperature swings from -40 to +180 degrees Fahrenheit, centrifugal forces that would instantly kill any human, and electromagnetic interference from the shell's own propellant. British scientists face additional constraints. The Royal Navy demands any proximity device weigh less than 3 pounds, cost under $50, and function reliably after months of shipboard storage in tropical humidity. These requirements seem mutually exclusive. Sophisticated electronics are delicate and expensive, while rugged components lack the precision needed for split-second targeting. Expert consensus emerges. Electronic proximity fusing represents an interesting theoretical exercise, but offers no practical military application. Dr. Edward Teller, architect of the hydrogen bomb, dismisses proximity fusing as an engineering fantasy that distracts from achievable solutions. The National Academy of Sciences concludes that traditional time fuses, while imperfect, represent the maximum achievable anti-aircraft effectiveness given physical limitations. The stakes couldn't be higher. Intelligence reports suggest Germany is developing jet aircraft and guided missiles that will render traditional anti-aircraft fire completely obsolete. Without a breakthrough in defensive technology, American bombers, and the men flying them, face certain slaughter over Nazi-occupied Europe. The projected casualties are staggering. 70% losses within 6 months. Into this environment of scientific despair and military urgency steps an unlikely figure. He carries no weapons engineering credentials, no military rank, no formal electronics training. His background is in cosmic ray research, studying particles from deep space that most Americans have never heard of. But Merle Tuve is about to prove that sometimes the most revolutionary solutions come from the least expected sources. His office at the Carnegie Institution in Washington, D.C. overflows with electronic equipment that looks more like science fiction than serious research. Vacuum tubes glow amber in jury-rigged assemblies, their filaments casting eerie shadows on walls covered with incomprehensible mathematics. Colleagues whisper that Tuve builds contraptions nobody else understands to study phenomena nobody else cares about. March 4, 1940. Tuve receives an urgent telegram from Dr. Vannevar Bush, director of the newly formed National Defense Research Committee. Report to Navy Department immediately for consultation on anti-aircraft defenses. Tuve assumes he's being asked to contribute his expertise in electronics to someone else's proximity fuse project. The reality is far more dramatic. Tuve walks into a conference room filled with America's most prominent weapons scientists and discovers they're expecting him to solve the proximity fusing problem single-handedly. Admiral Harold Bowen, Chief of Naval Research, slides a thick folder across the mahogany table. Doctor, we've reviewed your cosmic ray instrumentation. Your equipment functions in conditions that destroy everything we build. Tuve opens the folder, and his trained physicist's mind immediately grasps what the weapons experts have missed. The proximity fusing problem isn't fundamentally about weapons. It's about miniaturized electronics operating in extreme environments. Every technique he's developed for cosmic ray research applies directly to artillery shells. This is a radio proximity detector, Tuve says quietly, sketching circuits on the conference room blackboard. The shell contains a small radar transmitter. When radio waves reflect off the target aircraft, the return signal triggers detonation. The room falls silent as America's weapons experts study his crude diagram. Admiral Bowen leans forward. Doctor, how long would development take? 18 months for a working prototype, Tuve replies. Assuming we can solve the ruggedization issues. The Admiral's face hardens. Doctor, you have 6 months. After that, we may not have a Navy left to protect. What Admiral Bowen doesn't tell Tuve is that naval intelligence has identified German submarine wolf packs assembling for coordinated attacks on American shipping. Without effective anti-aircraft defense, American supply convoys face annihilation. The margin for error has disappeared. Merle Tuve nods slowly, adjusting his spectacles. He has just accepted responsibility for creating the most sophisticated electronic device ever mass-produced, in less time than it typically takes to design a new automobile. The fate of the free world now rests with a cosmic ray researcher who's never fired a gun in his life. The technical challenges seem insurmountable. A proximity fuse must house a complete radio station, transmitter, receiver, antenna, power supply, and detonation circuit within a package smaller than a coffee can. The electronics must survive being fired from a gun with an acceleration equivalent to being dropped from a 10-story building onto concrete, then function flawlessly while spinning at 500 revolutions per second in sub-zero temperatures. Tuve's first prototype looks like a metallic soup can stuffed with glowing vacuum tubes. On May 15, 1940, the team conducts their inaugural test at the Dahlgren Naval Proving Grounds. The shell contains a simple radio altimeter designed to detonate when it senses the ground approaching. Basically, an electronic version of a traditional time fuse, but one that automatically adjusts for terrain variations. The 5-inch naval gun thunders. The prototype shell arcs gracefully over the Potomac River, its tiny radio transmitter functioning perfectly despite the brutal launch forces. At precisely 3,000 feet altitude, the electronic brain calculates its distance from the water below and triggers detonation. The explosion creates a perfect orange fireball exactly where traditional calculations predicted the shell should explode, proving that electronics can indeed survive the violence of artillery firing. But surviving is not enough. Tuve needs his device to actively hunt aircraft, not simply measure altitude. This requires radio waves that can distinguish between an aluminum airplane and the ground below, electronic circuits that can process reflected signals in milliseconds, and power supplies that function reliably while subjected to forces that would instantly kill any human. The breakthrough comes from an unexpected source. Dr. Van Allen, experimenting with radio frequencies, discovers that aircraft reflect electromagnetic energy differently than terrain. At specific wavelengths, an airplane creates a distinctive radio signature that electronic circuits can recognize and track. Better yet, this signature strengthens as the shell approaches its target, providing a natural guidance system. On June 21, 1940, Tuve watches nervously as technicians load his latest prototype into the test gun. This shell contains not just radio altitude detection, but active target tracking, a miniaturized radar system that should theoretically explode when it approaches any aircraft within lethal range. The gun fires. The shell climbs toward a radio-controlled target drone cruising overhead at 200 miles per hour. For 3 agonizing seconds, nothing happens. Then the sky erupts in a brilliant flash as the proximity fuse detonates just 50 feet from the target drone, shredding its wings with a cloud of steel fragments. Tuve removes his protective goggles and allows himself a rare smile. He has just created the world's first smart munition, a shell that can think, hunt, and kill autonomously. Now he has to convince the bureaucrats not to shut him down. Admiral William Blandy, chief of the Bureau of Ordnance, riffles through the proximity fuse documentation with obvious skepticism. Dr. Tuve, these claims exceed credible performance parameters. You're suggesting a single electronic device can improve anti-aircraft effectiveness by a factor of 10? The mathematics are solid, Admiral, Tuve replies quietly. Traditional time fuses require precise predictions of aircraft position several seconds in the future. Proximity fusing eliminates that guesswork by reacting to the actual target location. Dr. Clarence Hickman, chief scientist at the Aberdeen Proving Ground, leans forward with barely concealed contempt. Doctor, with respect, you're a cosmic ray researcher, attempting to revolutionize military ordnance. We've been developing artillery fuses since 1903. What makes you think you can solve problems that have confounded weapons experts for 4 decades? The room erupts. Colonel James Crockett, representing Army Ordnance, slams his folder shut. This is exactly the kind of academic theorizing that wastes critical resources. We need practical improvements to existing systems, not science fiction fantasies. Admiral Harold Bowen raises his hand for silence, but the damage is done. General Carl Spaatz, soon to command strategic bombing operations in Europe, stands dramatically. Gentlemen, every month we delay practical weapons development costs American lives. I cannot support diverting resources from proven technologies to chase theoretical possibilities. Dr. Edward Teller, the theoretical physicist who will later design the hydrogen bomb, delivers the most devastating critique. The proximity fuse violates fundamental principles of reliability engineering. Complex electronic systems fail predictably. It's a statistical certainty. Do we really want our defensive capabilities dependent on delicate vacuum tubes and experimental circuits? Tuve feels the project dissolving before his eyes. These men control America's weapons development budgets. Their rejection would mean immediate termination of proximity fuse research, just as German submarine attacks on American shipping reach crisis proportions. But then Admiral Bowen speaks. Harold Bowen is a rarity in the peacetime Navy, an officer who rose through the ranks based on technical competence rather than political connections. He served as a naval engineer before commanding destroyers in the Pacific, giving him practical experience with both electronics and anti-aircraft gunnery. Gentlemen, Bowen says quietly, I've reviewed Dr. Tuve's test results personally. I've also reviewed our current anti-aircraft effectiveness reports. He slides a classified folder across the table to General Spaatz. Sir, if you examine the casualty projections for unescorted bomber operations over Germany, you'll find that our current defensive systems provide essentially zero protection against high-speed aircraft. The room falls silent as military officers study these statistics none of them want to acknowledge, publicly. Against German fighters attacking at 400 miles per hour, American anti-aircraft guns achieve approximately 1 kill per 6,000 shells fired. The mathematics are simple and terrifying. American bombers will be annihilated long before inflicting meaningful damage on German industrial targets. Admiral Bowen continues, Dr. Tuve isn't proposing to improve our existing systems. He's proposing to replace them with something that actually works. Based on test results, proximity-fused shells achieve kill ratios 15 times higher than conventional ammunition. General Spaatz studies the classified documents, his face growing pale. The projected bomber losses over Germany approach 80% within the first 6 months of operations. Admiral, he says slowly, these numbers suggest our entire strategic bombing doctrine may be obsolete. Exactly, Bowen replies, which is why Dr. Tuve's research represents our highest defense priority. Dr. Hickman objects strenuously. Admiral, you're asking us to bet American lives on untested electronic devices built by physicists. This is madness. The room erupts again, with experts shouting over each other about reliability, cost, manufacturing complexity, and security concerns. Through the chaos, Admiral Bowen's voice cuts like a blade. Gentlemen, I am authorizing full-scale development of the proximity fuse effective immediately. Dr. Tuve, you have unlimited resources and top priority classification. He stands, gathering his papers. This meeting is concluded. As the experts file out, muttering about reckless decisions and wasted appropriations, Admiral Bowen approaches Tuve privately. Doctor, he says quietly, you have 18 months to prove them wrong. After that, we'll all know whether American bomber crews live or die based on your cosmic ray experiments. Tuve adjusts his spectacles nervously. He has just been handed the resources to create the most advanced weapons system in human history, and the responsibility for every American airman who will depend on it for survival. If you're fascinated by the untold stories of World War II's secret weapons, make sure to subscribe and hit that notification bell. We're diving deep into the classified technologies that changed the course of history, and you won't want to miss what's coming next. January 5th, 1943. The Naval Gunnery Range at Dahlgren stretches across the frozen Potomac River like a testing ground for the apocalypse. Merle Tuve stands in the observation bunker, watching technicians load his latest proximity fuse prototypes into a 5-inch naval gun. After 30 months of development, the VT fuse has evolved from a crude electronic experiment into a miniaturized marvel of engineering. The statistics from preliminary testing stagger military observers. Traditional time-fused anti-aircraft shells achieve hits on 2% of targets under ideal conditions. Tuve's proximity-fused shells demonstrate a 52% hit rate, a 26-fold improvement that transforms anti-aircraft defense from desperate guesswork into lethal precision. But laboratory success means nothing without combat validation. Admiral Chester Nimitz, commander of Pacific Fleet Operations, demands absolute proof before equipping American warships with untested electronics. The testing protocol is brutal. Live fire exercises against full-speed aircraft flown by experienced pilots under realistic combat conditions. Lieutenant Commander William Wild Bill Alt pilots his SBD Dauntless dive bomber through the designated target zone at 250 miles per hour, practicing evasive maneuvers that have kept him alive through 2 years of Pacific combat. Below him, the cruiser USS Helena tracks his approach with newly installed VT-fused anti-aircraft guns. The first proximity-fused shell detonates 75 feet from Alt's aircraft, close enough that shrapnel peppers his wings, but far enough away to avoid serious damage. The second shell explodes directly beneath his dive bomber, creating a cloud of steel fragments that would have shredded any enemy aircraft. Alt's radio crackles with amazement. Jesus Christ, that thing exploded right under me. How did it know where I was? The answer lies in physics that most naval officers barely comprehend. Each shell broadcasts radio waves in a precise pattern, creating an invisible detection zone around the projectile. When these waves reflect off an aircraft's metal structure, they return to the shell's receiver with characteristics that reveal the target's distance, direction, and approach speed. Electronic circuits process this information in thousandths of a second, triggering detonation at the optimal moment for maximum destruction. Testing accelerates as combat reports from the Pacific reveal the desperate need for improved anti-aircraft defense. Japanese kamikaze pilots exploit a lethal weakness in American naval formations: the gap between maximum effective range of shipboard fighters and minimum arming distance of anti-aircraft shells. In this deadly zone, enemy aircraft can attack virtually unimpeded by defensive fire. June 12, 1944. The destroyer USS William D. Porter conducts the first operational test of proximity-fused ammunition during anti-aircraft exercises near Pearl Harbor. Captain Wilfred Walter orders his gunners to engage radio-controlled target drones using both conventional time fuses and experimental VT shells. The results are decisive. Time-fused shells require an average of 1/200 rounds to destroy a single target, while proximity-fused shells achieve kills with just 150 rounds, an 8-fold improvement in ammunition efficiency. More importantly, proximity-fused shells proved devastatingly effective against multiple targets attacking simultaneously. Traditional anti-aircraft doctrine requires gunners to estimate each target's future position and set individual time fuses accordingly, a process that breaks down completely when facing coordinated attacks by numerous aircraft. Proximity shells automatically adjust to each target they encounter, creating a defensive umbrella that destroys attackers regardless of their specific flight paths. Japanese pilots noticed the difference immediately. Flight Petty Officer Saburo Sakai, a veteran of 50 combat missions, reports a disturbing new phenomenon during attacks on American naval formations. Enemy shells now explode without hitting anything. It is as if they can sense our aircraft approaching. Many pilots refuse to attack American ships because the anti-aircraft fire has become too accurate. The moment of ultimate validation arrives during the largest carrier battle in naval history, June 19, 1944, dawn. The Battle of the Philippine Sea begins as Japanese Admiral Jisaburo Ozawa launches 373 carrier aircraft against American Task Force 58, commanded by Vice Admiral Mark Mitcher. What happens next demonstrates the proximity fuse's revolutionary impact on naval warfare. American anti-aircraft gunners, equipped with VT-fused ammunition, create a wall of exploding steel that Japanese pilots describe as impossible to penetrate. Unlike previous naval battles where aircraft could approach ships by flying between shell bursts timed to explode at fixed altitudes, proximity-fused shells actively hunt attacking aircraft, exploding at precisely the right moment to maximize destruction. The massacre is swift and total. In just 7 hours of combat, American anti-aircraft guns destroy 346 Japanese carrier aircraft, more planes than Japan shot down during the entire Pearl Harbor attack. Japanese pilots radio increasingly desperate reports. Anti-aircraft fire too heavy to continue attack. Shells exploding all around us. Cannot reach American ships. Lieutenant J.G. Alex Vrasiu, flying combat air patrol in his F-6F Hellcat, watches the slaughter with professional admiration. Their anti-aircraft fire was so thick you could almost walk on it. Every shell seemed to explode right where the Japanese planes were flying. I've never seen anything like it. The statistics are staggering. American naval forces fire 36,370 anti-aircraft rounds during the battle. Although only 25% use proximity fuses, these VT-fused shells account for 51% of all aircraft destroyed by shipboard gunners. Despite representing a quarter of the ammunition expended, they achieve over half the kills. Japanese losses are catastrophic. 476 aircraft destroyed, 3 aircraft carriers sunk, and Japan's naval aviation capability effectively eliminated as an offensive threat. American pilots nicknamed the engagement the Great Marianas Turkey Shoot, because enemy aircraft fall from the sky with such regularity that aerial combat resembles hunting defenseless game birds. But the proximity fuse's greatest test still lies ahead, against German jets moving at speeds that dwarf anything Japanese pilots could achieve. We're approaching the climax of this incredible story, how Merle Tuve's impossible invention turned the tide against Nazi Germany's most advanced weapons. Don't go anywhere, because what happens next in European skies will leave you speechless. Unlike traditional artillery that explodes only upon impact with the ground, proximity-fused shells detonate in precise airbursts above German positions, spraying deadly shrapnel downward through foxholes and trenches that would otherwise provide protection. German soldiers report shells that explode in the trees with devastating effect. Wehrmacht casualties from American artillery increased by 700% virtually overnight. Obergefreiter Klaus Weber, a German machine gunner who survived the Eastern Front, writes in his final letter home, "The American shells now explode above our heads. There is nowhere to hide. We cannot understand this new weapon that kills without touching the ground." By war's end, American factories produce over 22 million proximity-fused shells, more electronic devices than had been manufactured in all of human history combined. The program consumes resources second only to the Manhattan Project, requiring specially constructed factories, thousands of trained technicians, and raw materials allocation that strains the entire American industrial complex. The strategic impact proves decisive. In the Pacific, proximity-fused anti-aircraft fire maintains a 70% success rate against kamikaze attacks, saving countless American lives and preserving naval superiority that enables the final assault on Japan. In Europe, VT-fused artillery eliminates German defensive advantages, allowing Allied ground forces to advance with casualties far below predicted levels. German weapons experts, analyzing captured proximity fuses after the war, express stunned admiration for American electronic sophistication. Dr. Herbert Wagner, chief designer of German-guided missiles, admits, "We attempted similar proximity devices but never achieved reliable miniaturization. American electronics represent a manufacturing capability we could not match." Merle Tuve receives the Presidential Medal for Merit, the highest civilian honor for wartime service. President Harry Truman personally presents the award, calling proximity fusing a triumph of American scientific innovation that saved the lives of countless servicemen. But Tuve deflects personal credit, insisting the achievement belongs to his entire research team. The cosmic ray researcher, who revolutionized warfare, returns quietly to fundamental physics research, rarely discussing his military contributions. When pressed by reporters about his role in developing proximity fusing, Tuve responds with characteristic modesty. "I simply applied existing scientific principles to solve an engineering problem. The real heroes are the young men who used these devices in combat." Post-war analysis reveals proximity fusing's staggering contribution to Allied victory. Military. Historians estimate that traditional anti-aircraft defenses would have required 500,000 additional shells to achieve the same effectiveness as 22 million VT-fused rounds. More significantly, without proximity fusing, American bomber losses over Germany would have approached 90%, levels that would have made strategic bombing militarily impossible. Modern weapon systems, from Patriot missiles to naval close-in weapon systems, employ proximity detection principles pioneered by Tuve's wartime research. Today's smart munitions trace their lineage directly to the VT fuse, the first weapon that could think, adapt, and kill with electronic precision. Staff Sergeant Robert Murphy, a B-17 tailgunner who survived 35 missions over Germany, wrote to Tuve in 1947, "Dr. Tuve, you probably don't remember me, but I was one of thousands of airmen whose lives you saved with your proximity fuse. Every time we flew through Flak that exploded all around us instead of hitting us directly, we owed our lives to your invention. Because of you, we came home. Thank you." Merle Tuve died in 1982, having transformed warfare forever while remaining virtually unknown to the American public. His legacy lives on in every precision-guided weapon that protects American forces today. Proof that sometimes the most unlikely heroes achieve the most extraordinary victories.